Okay, so this is our third lab, the one on heat and thermodynamics, the gas laws, and also the specific heat capacity of copper. Okay. Um, all right, let's start off with the specific heat capacity. Okay. Specific heat capacity. Okay, let's just say a couple words about this before we begin. Okay. Suppose I have, let's just do an example. Suppose I have 1 gram of copper. Okay. And suppose I have 1 gram of aluminum. Okay. And suppose I have, doesn't matter, 1 gram, excuse me, 1 gram of magnesium, Mg. Okay. Now, suppose I add some heat to it. I'm going to add heat. Okay. Add some heat. And let's say I use 100 units. We haven't talked about what the units are. Suppose I add 100 units of heat to this. Okay. 100 heat. Okay. And again, we add 100 units of heat, whatever the units are. Okay. Well, it's clear that the temperature of the temperature of the copper will go up. It's clear that the temperature of the aluminum will go up, and it's clear the temperature of the magnesium will go up. But they'll all go up by a different amount because they're different substances. Okay, my pen keeps failing me by a different amount. I'll say delta T, different amount for each substance. The quantity that characterizes how much each substance's temperature goes up is called the specific heat capacity. Okay, so this is somehow going to be a measure of how a system's a certain substance's temperature changes with with adding heat to it. Okay, well, let's say I'm going to say delta T for a system. Let's try to do this in words, right? Delta T for the system is going to change depending on how much heat you add. Right? Heat added. Okay. The more heat you add, the greater the temperature goes up. So they're proportional to each other. Okay. All right. Now, suppose I added 100 units of heat. I'll pick the aluminum right now, 100 units of heat to this piece of aluminum. And we know the temperature will go up. But instead of 1 gram, suppose we made this 1 kilogram. Well, again, the temperature is going to go up, but it's not going to go up by the same amount. It's going to go up a lot less. Why? Because I have more mass. So the more mass you have, the smaller the change in temperature, delta T. And the way we say that mathematically is we put the mass in the denominator. Okay? Okay? So the more mass you have, then this side becomes smaller, right? Because if that's bigger, this fraction becomes smaller, and the temperature change is thus smaller. Okay. The other thing we need is, look, we have copper, we have aluminum, we have magnesium, and so somehow the change in temperature must depend on which substance, right? Which substance. So we're going to put a thing here, C. Okay, C is called the specific heat capacity. My pen, okay. Specific heat capacity. Okay, and it's going to be different for every substance. Okay. If we solve this Oh, well, the heat added, I'm going to call it Q. Okay, we usually use this symbol Q. This is M. Okay, so our equation looks like this. Delta T is equal to Q divided by MC. Now, I usually rewrite this because it's easy to remember that the heat added, Q, that's the heat. We haven't talked about the units yet. Heat is equal to MC, like MC Hammer, the rapper, delta T. Okay, this is usually how I write the equation. Okay, Q is equal to MC, specific heat capacity, the mass, and the change in temperature. Okay, but what is Q? Q is heat, energy. Okay, and so we need a unit to measure energy, right? What units are we going to use? Okay, my pen keeps going away. What units are we going to use? And the answer is we're going to use units that they used in historically. Okay, we're going to define something called a calorie. And that's with a little c. You'll see what I mean in a second, calorie. And this is going to be heat energy, unit of heat energy, unit of heat energy. Really, it's a unit of any type of energy, but we use it for heat all the time, heat energy. Okay? 1 calorie, with a small c, 1 calorie, is equal to the heat needed, heat energy needed to raise the temperature I'm just going to write temp, of 1 gram of water by 1 degree Celsius. Okay, that's the definition. The heat energy needed to raise temperature of 1 gram of water by 1 degree Celsius. Now, on the side, I'll tell you what a BTU is. That's also a heat energy unit. This is called a British thermal unit. BTU is a British thermal unit. And that's the heat needed. I'm just going to write heat needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit. Okay? So a BTU is actually bigger than a calorie. It's just another unit of energy. Okay, it's like going between centimeters and inches for length. They both measure length. They're just different units. Okay, so the 1 calorie is the heat energy needed to raise temperature of 1 gram of water by 1 degree C. Now, suppose I had 1 gram of aluminum, and I'm going to make this number up. Well, then the specific heat capacity for aluminum would be, and I'm making this up, say 0.28 calories per gram per degree C. Now, I don't know what the number is for aluminum. I don't really know. But let me explain. So this number means it only takes 0.28 calories of heat to raise the temperature of 1 gram of water by 1 degree Celsius, 0.28. See, it doesn't take as much as for water, okay? Magnesium, it would be 0.37 or some other number. So every substance has its own specific heat capacity, okay? All right. So again, our equation is the heat you add in calories is equal to the mass of the object times the specific heat capacity of the object times delta T, the change in temperature. Delta T is the change in temperature, okay? Change in temperature. And if we look for the change in temperature, if we solve this for delta T, again, it's equal to Q, the heat added, divided by the mass, and then the specific heat capacity. Okay. Now, in this lab, we want to find the specific heat capacity of water, copper, sorry. Okay. So the specific heat capacity of water, we just said, it's 1 calorie you need to add to 1 gram of water to raise the temperature by 1 degree Celsius. Okay, so we don't need a 1 there. 1 calorie per gram per degree C is the specific heat capacity of water. Now, I keep saying small c. Just as an aside, capital C, a capital calorie with a capital C, is equal to 1,000 little calories. With the small, I didn't make this up. This is chemist calorie. Okay. This with a capital C is called the food calorie. So when you say, oh, how many calories is this peanut? This is in food calories. This is called the food calorie. And so this is equal to 1,000 calories, which is 1 kilocalorie, kilocalorie. Okay, it's 1,000 of the little calories. So just keep that in mind in case you ever get asked anything about that. Okay, so in our lab, what we're going to do is we want to find a specific heat capacity, C, of copper. Okay, how can we do that? All right, well, that's a good question. Well, what we're going to do is we're going to take a piece of copper, copper, and we're going to heat it up. Okay, we're going to heat this up, put a flame under it, and make it very hot. So now we have a hot piece of copper. Hot piece of copper. Okay, and we're going to take this hot piece of copper and we're going to put it in some water. Okay, now this water, let's say there's 20 milliliters. I don't care. Okay, 20 milliliters. We have the water. What we do first is we're going to measure the temperature of the water, T of the water. And this is room temperature. Okay, so I'm going to make this up. Suppose we find the temperature of the water is 23 degrees Celsius. Okay, we know how much water there is. Good. Okay, so now what do we do? Well, now we're going to take that water. We're going to take this thing and we're going to put the hot piece of, place the hot piece of copper in there. Place hot piece of copper into the water. Okay. All right. So that's what we're going to do over here. Okay. So we're going to have our water. Oopsie, oopsie, oopsie. That's okay. I'll just make this into this. Okay. And here's our water. What did I say? 20 milliliters, whatever we put in. Okay. Well, we know the volume of water. That's key. Now we're going to have this hot piece of copper in there. And what's going to happen is the piece of copper is going to give off heat. That's what this squiggly line is. I'm going to call that Q. Okay, so Q is going to be the heat given off by the copper. Given off by the copper. And the heat given off by the copper is going to be the same as the heat absorbed by the water. Now, we don't know how much heat that is. How much is this? But we can figure it out. How much is this? How much heat? Well, that's easy to figure out, okay? Because remember, we have our equation. Q equals mc delta T. Now, if we do this for water, remember, this is going to be the heat that's absorbed by the water. It's the heat absorbed by the water is the same as the heat given off by the copper. Okay, so this Q will be the same as the copper is given off. Okay, now we know the mass of the water. If there's 20 milliliters, that means there's 20 grams of water. 1 milliliter of water, 1 ml of water is the same as 1 gram of water. Okay, so 20 milliliters is 20 grams of water. So we know M. We know the specific heat of water, right? C of water was 1 calorie per gram per degree C. And now we can measure delta T, right? If the T of the room, which is the same as the T of the water, right? The water's at room temperature. And we said, we made this up, was 23 degrees Celsius. Okay. When we put the hot copper in, what's going to happen is the temperature of the water, T of the water, is going to go up. Why is it going up? Because you have the hot copper in there. Okay. So let's say now the new temperature of the water is, I'll make this up, all right, 30 degrees C. Okay. That means we figure out delta T would be 7 degrees Celsius. So now we can figure out the heat absorbed by the copper, by the water. Heat absorbed this is my example, right? Absorbed by water. Okay. So Q is equal to M, which we said was, so M C of the water times delta T. So if we put in our numbers that we just made up, this is equal to M, we said was 20 grams, times the specific heat of water, which we said was 1 calorie per gram per degree C. And now we said delta T was 7 degrees, right? Delta T was 7 degrees up here, times 7 degrees Celsius. Okay, so this is my example. Notice degrees Celsius goes out, grams goes out, and we're left with just calories because it should be heat. So we get 20 times 7. So this would be 140 calories. Okay. So this is the heat absorbed by the water But remember, the heat absorbed by the water is also equal to the heat given off by the copper. By copper. Okay? So now for copper, remember, this was for water. This was for the water. For the copper now, right, we've got Q equals MC delta T. Okay. And again, we know the delta T of the copper. Okay. Because we know the initial temperature. Okay. Now we know the mass of the copper. We get the mass. And we just calculated this Q. Okay. And so we would have that C is just equal to Q divided by M delta T. Okay. And this would be for copper. So we can work out the specific heat capacity of copper by using this idea that the heat given off by the copper is equal to the heat absorbed by the water. And then we measure the temperature change of the water. We know specific heat of the water and so forth. Okay, so that's the experiment. The second part of the lab deals with the gas laws. okay? And the gas laws really are really this. This is what all the gas laws say. And there's 3 gas laws, but really it says this, that if you take the pressure of a gas, multiply by its volume, and divide by its temperature, temperature must always be in Kelvin. Okay. Remember, Kelvin is equal to 273 degrees, point something, I don't care, plus whatever the temperature is in Celsius. So if the temperature is 30 degrees Celsius, then that's equal to, what is that, 303 Kelvin. Okay, we could put degrees, even though they don't use degrees. Okay, so temperature must be in Kelvin. And so the gas laws say that the pressure times the volume divided by the temperature never changes. It's a constant, never changes. This ratio never changes. So if this ratio, PV over T, is 30, then no matter what I do to P, no matter what I do to V, and no matter what I do to T, it must always be 30. So this ratio never changes in whatever problem we're doing. Okay, now, if we change the pressure, we start with a pressure P1, and we start with a volume V1, and we start with a temperature T1 in Kelvin, right? Then that means if we change the pressure, make it P2, change the volume, make it V2, change the temperature T2, we must still get the same number because this ratio, PV over T, does not change, does not change. Okay? So historically, different people looked at this gas equation, and one thing that was done was by a fellow by the name of Boyle. Okay, and Boyle said, well, if T1 equals T2, which is a constant, so if you don't change the temperature, then we have P1 V1 over T equals P2 V2 over T. Well, the T's just go out. And so we end up with P1 V1 is equal to P2 V2. And this special case is known as Boyle's law. So Boyle's law is constant temperature. Okay, and this is an inverse relation. That means if you made, I'll write it here, P1 V1 equals P2 V2. It means, suppose if I double the pressure, then the volume has to be half. So that number doesn't change. If I made the pressure 1/6 as great, that means the volume has to be 6 times greater. So the 6's go out and it doesn't change. Here, the 2's would go out. So this is known as an inverse relation. And if we plot this, if we plot it, you should know this for the T's exam. It doesn't matter if I put P or V, it doesn't really matter on which axis. An inverse relation looks like this, you see? As the volume increases, the pressure is getting smaller. And as you decrease the volume, the pressure goes up. So this would be the graph for an inverse relation, or this would be the graph for Boyle's law. Okay, again, Boyle's law, T is a constant. Okay. The second special case of the gas law is if the pressure doesn't change, if P1 equals P2. Okay. And this was done by somebody named of Charles. So this is called Charles's law. Okay. So again, if we have P V1 over T1 equals P V2 over T2. So P1 equals P2 equals just P, right? The P's go out, and we end up with this relation. The volume over the temperature doesn't change. Remember, T is in Kelvin. The volume and pressure can be in any units. T, oopsie, come on, pen. T2. Okay, so I'm going to write that P, V, any units. That's a P. Okay, any units you can use. But T must be Kelvin. You cannot do your calculations in Celsius or Fahrenheit. Okay, must be in Kelvin. Okay, this type of relationship is called a direct relationship. Okay, so again, this is Charles' law. And that's P equals a constant. Charles can't take the pressure. Okay, and it's direct because if I made this 7 times the volume, then the temperature must increase by 7 times, so it doesn't change. If I made the volume 1/4, then the temperature has to be 1/4. They do it directly the same because then this 1/4 goes out and the ratio stays the same. So if we plot a direct relationship, it just looks like this. So this would be V and this would be T, or T and V. It doesn't matter which way you go, right? Looks like a straight line. One increases, the other increases. One decreases, the other decreases by the same amount. Okay. And then finally, the third law that we talk about, if we take the gas laws here, if we take the volume as a constant, so it's a constant, then our gas law becomes P1 V divided by T1 is equal to P2 times V divided by T2. And once again, the V's will go out and we end up with an equation that looks very much like Charles' law, but it has pressure in it. P1 over T1 equals P2 over T2. Again, the pressure, you can use any units, atmospheres, pascals, any units you want. Pounds per square inch, doesn't matter, but T must be in Kelvin. Okay. And again, so this is the law of Gay-Lussac. Gay-Lussac, if we're French, Lussac. Okay. And this just tells that the volume is a constant. And this is also a direct relationship. Okay, it's a direct relation. So once again, if we made this 12 times the pressure, then this must be 12 times the temperature. And again, so that'll go out and you keep the same ratio. If we make this 1/5 the pressure, then this must be 1/5 the temperature. Whatever you do to one, you have to do exactly to the other. That's why it's a direct relationship, okay? This way that goes out and you still have the same ratio, okay? And again, so a plot of the Gay-Lussac law would have P and T, or T and V, it doesn't matter. And again, a straight line. When one increases, the other increases. When one decreases, the other one decreases. Okay? In class and on Collaborate, I'll do a bunch of examples for these 3 laws. Okay? That's it.